Welcome to Flourish. I'm Diane Planidin, and you're in the right place if you're a great inspired life. And we do so by working on our own personal development so we can be strong role models for those we love and mentor, and strong for our own selves, keep that energy flowing. Today, we are on week 1, chapter 3 of Psychology 100 from Queen's University, thinking like a psychological scientist. So let's get started. We are bombarded every day with claims about how the world works, claims that have a direct impact on how we think about and solve problems in society and our personal lives. This module explores important considerations for evaluating the trustworthiness of such claims by contrasting between scientific thinking and everyday observations, also known as anecdotal evidence. The learning objectives for this chapter are as follows. Compare and contrast conclusions based on scientific and everyday inductive reasoning. Understand why scientific conclusions and theories are trustworthy, even if they're not able to be proven. Articulate what it means to think like a psychological scientist, considering qualities of good scientific explanations and theories. And finally, discuss science as a social activity, comparing and contrasting the facts and values. As usual, keep in mind that these questions I just talked about is because I'm a student and I'm learning. I'm not a teacher. So this is what I keep in the back of my mind as I study. So, introduction. Why are some people so much happier than others? Is it harmful for children to have imaginary companions? How might students study more effectively? Even if you've never considered these questions before, you probably have some guesses about their answers. Maybe you think getting rich or falling in love leads to happiness. Perhaps you view imaginary friends as expressions of a dangerous lack of realism. What's more, if you were to ask your friends, they would probably also have opinions about these questions, opinions that may differ from your own. A quick internet search would yield even more answers. We live in the information age with people having access to more explanations and answers than at any other time in history. But although the quantity of information is continually increasing, it's always good practice to consider the quality of what you read or watch. Not all information is equally trustworthy. The trustworthiness of information is especially important in an era where fake news, urban myths, misleading clickbait, and conspiracy theories compete for our attention alongside well informed conclusions grounded in evidence. Determining what information is well informed is a crucial concern and a central task of science. Science is a way of using observable data to help explain and understand the world around us in a trustworthy way. In this module, you will learn about scientific thinking. You will come to understand how scientific research informs our knowledge and helps us create theories. You will also come to appreciate how scientific reasoning is different from the types of reasoning people often use to form personal opinions. Scientific versus everyday reasoning. Each day, people offer statements as if they are facts, such as, "It looks like rain today," or "Dogs are very loyal." These conclusions represent hypotheses about the world, best guesses as to how the world works. Scientists also draw conclusions, claiming things like, there's an 80% chance of rain today, or dogs tend to protect their human companions. You'll notice that the two examples of scientific claims use less certain language and are more likely to be associated with probabilities. Understanding the similarities and differences between scientific and everyday non scientific statements is essential to our ability to accurately evaluate the trustworthiness of various claims. Scientific and everyday reasoning both employ induction, drawing general conclusions from specific observations. For example, a person's opinion that cramming for a test increases performance may be based on her memory of passing an exam after pulling an all night study session. Similarly, a researcher's conclusion against cramming might be based on studies comparing the test performances of people who studied the material in different ways. For example, cramming versus studying sessions spaced out over time. In these scenarios, both scientific and everyday conclusions are drawn from a limited sample of potential observations. The process of induction alone does not seem suitable enough to provide trustworthy information, given the contradictory results. What should a student who wants to perform well on exams do? One source of information encourages her to cram, while another suggests that spacing out her studying time is the best strategy. To make the best decision with the information at hand, we need to appreciate the differences between personal opinions and scientific statements, which requires an understanding of science and the nature of scientific reasoning. There are generally agreed upon features that distinguish scientific thinking and the theories and data generated by it from everyday thinking. A short list of some of the commonly cited features are as follows of scientific theories. Accuracy. Explanations and theories match real world observations. For example, although people say opposites attract, theories that focus on the role of partner similarity do a better job of explaining the observed data. Consistency. A theory has few exceptions and shows agreement with other theories within and across disciplines. For example, the theory of evolution explains many findings across biology and psychology, predicting, for example, that humans are better able to solve problems presented in concrete rather than abstract terms. Scope. The extent to which a theory extends beyond currently available data, explaining a wide array of phenomena. For example, there is a theory that people use mental shortcuts when making decisions rather than weighing every single piece of evidence. This can be seen in consumer purchasing behavior, in romantic relationships, in charitable donations, and in health choices. Simplicity. When multiple explanations are equally good at explaining the data, the simplest should be selected. For example, the simplest explanation for why good people sometimes do bad things is because they succumb to some outside influence. And fruitfulness, the usefulness of the theory in guiding new research by predicting new testable relationships. For example, the explanation that competition leads to improved performance can be tested by researching different types of competition. One additional feature of modern science not included in this list, but prevalent in scientists' thinking and theorizing, is falsifiability, a feature that has so permeated scientific practice that it warrants additional clarification. In the early 20th century, Karl Popper suggested that science can be distinguished from pseudoscience, or just everyday reasoning, because scientific claims are capable of being falsified. That is, a claim can be conceivably demonstrated to be untrue. For example, a person might claim that all people are right-handed. This claim can be tested and ultimately thrown out because it can be shown to be false. There are people who are left-handed. An easy rule of thumb is not to get confused by the term falsifiable, but to understand that more or less it means testable. On the other hand, some claims cannot be tested and falsified. Imagine, for instance, that a magician claims that he can teach people to move objects with their minds. The trick, he explains, is to truly believe in one's ability for it to work. When his students fail to budge chairs with their minds, the magician scolds, "Obviously, you truly don't believe." The magician's claim does not qualify as falsifiable because there is no way to disprove it. It is unscientific. Popper was particularly irritated about non-scientific claims because he believed they were a threat to the science of psychology. Specifically, he was dissatisfied with Freud's explanations for mental illness. Freud believed that when a person suffers a mental illness, it is often due to problems stemming from childhood. For instance, imagine a person who grows up to be an obsessive perfectionist. If she were raised by messy, relaxed parents, Freud might argue that her adult perfectionism is a reaction to her early family experiences, an effort to maintain order and routine instead of chaos. Alternatively, imagine the same person being raised by harsh, orderly parents. In this case, Freud might argue that her adult tidiness is simply her internalizing her parents' way of being. As you can see, according to Freud's rationale, both opposing scenarios are possible, no matter what the disorder. Freud's theory could explain its childhood origin, thus failing to meet the principle of falsifiability. Popper argued against statements that could not be falsified. He claimed that they blocked scientific progress. There was no way to advance, refine, or refute knowledge based on such claims. Popper's solution was a powerful one. If science showed all the possibilities that were not true, we would be left only with what is true. That is, we need to be able to articulate beforehand the kinds of evidence that will disprove our hypotheses and cause us to abandon it. This may seem counterintuitive. For example, if a scientist wanted to establish a comprehensive understanding of why car accidents happen, she would systematically test all potential causes: alcohol consumption, speeding, using a cell phone, fiddling with the radio, wearing sandals, eating, chatting with a passenger, etc. A complete understanding could only be achieved once all the possible explanations were explored and either falsified or not. After all the testing was concluded, the evidence would be evaluated against the criteria for falsification, and the only real causes of accidents would remain. The scientists could dismiss certain claims, for example, sandals lead to car accidents, and keep only those supported by research. For example, using a mobile phone while driving increases risk. It might seem absurd that scientists would need to investigate so many alternative explanations, but it is exactly how we rule out bad claims. Of course, many explanations are complicated and involve multiple causes, as with car accidents, as well as psychological phenomena. Although the idea of falsification remains central to scientific data and theory development, these days it's not used strictly the way Popper originally envisioned it. To begin with, scientists aren't solely interested in demonstrating what isn't. Scientists are also interested in providing descriptions and explanations for the way things are. We want to describe different causes and the various conditions under which they occur. We want to discover when young children start speaking in complete sentences, for example, or whether people are happier on the weekend, or how exercise impacts depression. These explorations require us to draw conclusions from limited samples of data. In some cases, this data seem to fit with our hypotheses, and in others, they do not. This is where interpretation and probability come in. The interpretation of research results. Imagine a researcher wanting to examine the hypothesis, a specific prediction based on previous research or scientific theory, that caffeine enhances memory. She knows there are several published studies that suggest this might be the case, and she wants to further explore the possibility. She designs an experiment to test this hypothesis. She randomly assigns some participants a cup of fully caffeinated tea and some a cup of herbal tea. All the participants are instructed to drink up, study a list of words, then complete a memory test. There are three possible outcomes of this proposed study. The caffeine group performs better, support for the hypotheses. The no caffeine group performs better, evidence against the hypotheses. There's no difference in the performance between the two groups, also evidence against the hypotheses. Let's look from a scientific point of view at how the researcher should interpret each of these three possibilities. First, if the results of the memory test reveal that the caffeine group performs better, this is a piece of evidence in favor of the hypotheses. It appears, at least in this case, that caffeine is associated with better memory. It does not, however, prove that caffeine is associated with better memory. There are still many questions left unanswered. How long does a memory boost last? Does caffeine work the same way with people of all ages? Is there a difference in memory performance between people who drink caffeine regularly and those who never drink it? Could the results be a freak occurrence? Because of these uncertainties, we do not say that a study, especially a single study, proves a hypothesis. Instead, we say the results of the study offer evidence in support of the hypotheses. Even if we tested this across 10,000 or 100,000 people, we could still not use the word proven to describe this phenomenon. This is because inductive reasoning is based on probabilities. Probabilities are always a matter of degree. They may be extremely likely or unlikely. Science is better at shedding light on the likelihood or probability of something than at proving it. In this way, data is still highly useful, even if it doesn't fit Popper's absolute standards. The science of meteorology helps illustrate this point. You might look at your local weather forecast and see a high likelihood of rain. This is because the meteorologist has used inductive reasoning to create her forecasts. She has taken current observations, lots of dense clouds coming towards your city, and compared them to historical weather patterns associated with rain, making a reasonable prediction of a high probability of rain. The meteorologist has not proven it will rain, however, by pointing out the oncoming clouds. Proof is more associated with deductive reasoning. Deductive reasoning starts with general principles that are applied to specific instances. The reverse of inductive reasoning. When the general principles or premises are true and the structure of the argument is valid, the conclusion is, by definition, proven. It must be so. A deductive truth must apply in all relevant circumstances. For example, all living cells contain DNA. From this, you can reason, deductively, that any specific living cell of an elephant or a person or a snake will therefore contain DNA. Given the complexity of psychological phenomena, which involves many contributing factors, it is nearly impossible to make these types of broad statements with certainty. The second possible result from the caffeine memory study is that the group who had no caffeine demonstrates better memory. This result is the opposite of what the researcher expects to find in her hypotheses. Here, the researcher must admit the evidence does not support her hypotheses. She must be careful, however, not to extend that interpretation to other claims. For example, finding increased memory in the no caffeine group would not be evidence that caffeine harms memory. Again, there are too many unknowns. Is this finding a freak occurrence, perhaps based on an unusual sample? Is there a problem with the design of the study? The researcher doesn't know. She simply knows that she was not able to observe support for her hypotheses. There is at least one additional consideration. The researcher originally developed her caffeine benefits memory hypotheses based on conclusions drawn from previous research. That is, previous studies found results that suggested caffeine boosts memory. The researcher's single study should not outweigh the conclusions of many studies. Perhaps the earlier research employed participants of different ages or who had different baseline levels of caffeine intake. This new study simply becomes a piece of fabric in the overall quilt of studies of the caffeine-memory relationship. It does not, on its own, definitively falsify the hypotheses. Finally, it's possible that the results show no difference in memory between the two groups. How should the researcher interpret this? How would you? In this case, the researcher once again has to admit that she has not found support for her hypotheses. Interpreting the results of a study, regardless of outcome, rests on the quality of the observations from which those results are drawn. If you learn, say, that each group in a study included only 4 participants, or that they were all over 90 years old, you might have concerns. Specifically, you should be concerned that the observations, even if accurate, aren't representative of the general population. This is one of the defining differences between conclusions drawn from personal anecdotes and those drawn from scientific observation. Anecdotal evidence derived from personal experience and unsystematic observations, for example, common sense, is limited by the quality and representativeness of observations and by memory shortcomings. Well-designed research, on the other hand, relies on observations that are systematically recorded, of high quality and representative of the population it claims to describe. Why should I trust science if it can't prove anything? It's worth delving a bit deeper into why we ought to trust the scientific inductive process, even when it relies on limited samples that don't offer absolute proof. To do this, let's examine a widespread practice in psychological science, null hypothesis significance testing. To understand this concept, let's begin with another research example. Imagine, for instance, a researcher is curious about the ways maturity affects academic performance. She might have a hypothesis that mature students are more likely to be responsible about studying and completing homework, and therefore will do better in their courses. To test this hypothesis, the researcher needs a measure of maturity and a measure of course performance. She might calculate the relationship, between student age, her measure of maturity, and points earned in a course, her measure of academic performance. Ultimately, the researcher is interested in the likelihood or probability that these two variables closely relate to one another. Null hypothesis significance testing assesses the probability that the collected data, the observations, would be the same if there were no relationship between the variables in the study. Use our example, the NHST, null hypothesis significance testing, would test the probability that the researcher would find a link between age and class performance if there were, in no reality, no such link. Now, here's where it gets a little complicated. NHST involves a null hypothesis, a statement that two variables are not related. In this case, that student maturity and academic performance are not related in any meaningful way. NHST also involves an alternative hypothesis, a statement that two variables are related. In this case, that student maturity and academic performance go together. To evaluate these two hypotheses, the researcher collects data. The researcher then compares what she expects to find, probability, with what she actually finds, the collected data, to determine whether she can falsify or reject the null hypotheses in favor of the alternative hypotheses. How does she do this? By looking at the distribution of data. The distribution is the spread of values, in our example, the numeric values of student scores in the course. The researcher will test her hypotheses by comparing the observed distribution of grades earned by older students to those earned by younger students, recognizing that some distributions are more or less likely. Your intuition tells you, for example, that the chances of every single person in the course getting a perfect score are lower than their scores being distributed across all levels of performance. The researcher can use a probability table to assess the likelihood of any distribution she finds in her class. These tables reflect the work over the past 200 years of mathematicians and scientists from a variety of fields. You can see in Table 2A, if you're watching this on YouTube, an example of an expected distribution if the grades were normally distributed. Most are average, and relatively few are amazing or terrible. In Table 2B, you can see possible results of this imaginary study and can clearly see how they differ from the expected distribution. In the process of testing these hypotheses, there are four possible outcomes. These are determined by two factors. One, reality, and two, what the researcher finds. See Table 3. We're getting there. The best possible outcome is accurate detection. This means that the researcher's conclusion mirrors reality. In our example, let's pretend the more mature students do perform slightly better. If this is what the researcher finds in her data, her analysis qualifies as an accurate detection of reality. Another form of accurate detection is when a researcher finds no evidence for a phenomenon, but that phenomenon doesn't actually exist anyway. Using this same example, let's now pretend that maturity has nothing to do with academic performance. Perhaps academic performance is instead related to intelligence or study habits. If the researcher finds no evidence for a link between maturity and grades and none actually exists, she will have also achieved accurate detection. There are a couple of ways that research conclusions might be wrong. One is referred to as a type 1 error when the researcher concludes that there is a relationship between two variables, but in reality, there is not. Back to our example. Let's now pretend there's no relationship between maturity and grades, but the researcher still finds one. Why does this happen? It may be that her sample, by chance, includes older students who also have better study habits and perform better. The researcher has found a relationship, the data appearing to show age as significantly correlated with academic performance. But the truth is that the apparent relationship is purely coincidental. The result of these specific older students in this particular sample having better than average study habits, the real cause of the relationship. They may have always had superior study habits, even when they were young. Another possible outcome of NHST, which is the null hypothesis, is a type 2 error when the data fail to show a relationship between variables that actually exists. In our example, this time, pretend that maturity is, in reality, associated with academic performance, but the researcher doesn't find it in her sample. Perhaps it was just her bad luck that her older students are just having an off day, suffering from test anxiety, or were uncharacteristically careless with their homework. The peculiarities of her particular sample by chance prevent the researcher from identifying the real relationship between maturity and academic performance. These type of errors might worry you that there is just no way to tell if data are any good or not. Researchers share your concern and address them by using probability values, p-values, to set a threshold for a type 1 or type 2 error. When researchers write that a particular finding is significant as p is less than 0.05 level, they're saying that if the same study were repeated 100 times, we should expect this result to occur, by chance, fewer than 5 times. That is, in this case, a type 1 error is unlikely. Scholars sometimes argue over the exact threshold that should be used for probability. The most common in psychological science are 0.05, 5% chance, 0.01, 1% chance, and 0.001, 1/10 of a 1% chance. Remember, psychological science doesn't rely on definitive proof. It's about the probability of seeing a specific result. This is also why it's so important that scientific findings be replicated in additional studies. It's because of such methodologies that science is generally trustworthy. Not all claims and explanations are equal. Some conclusions are better bets, so to speak. Scientific claims are more likely to be correct and predict real outcomes than common sense opinions and personal anecdotes. This is because researchers consider how to best prepare and measure their subjects, systematically collect data from large and, ideally, representative samples, and test their findings against probability. Scientific theories. The knowledge generated from research is organized according to scientific theories. A scientific theory is a comprehensive framework for making sense of evidence regarding a particular phenomenon. When scientists talk about a theory, they mean something different from how the term is used in everyday conversation. In common usage, a theory is an educated guess, as in, I have a theory about which team will make the playoffs, or I have a theory about why my sister is always running late for appointments. Both of these beliefs are liable to be heavily influenced by many untrustworthy factors, such as personal opinions and memory biases. A scientific theory, however, enjoys support from many research studies, collectively providing evidence, including but not limited to that which has falsified competing explanations. A key component of good theories is that they describe, explain, and predict in a way that can be empirically tested and potentially falsified. Theories are open to revision if new evidence comes to light that compels re-examination of the accumulated relevant data. In ancient times, for instance, people thought the sun traveled around the earth. This seemed to make sense and fit with many observations. In the 16th century, however, astronomers began systematically charting visible objects in the sky, and over a 50-year period, with repeated testing, critique, and refinement, they provided evidence for a revised theory. The Earth and other cosmic objects revolved around the sun. In science, we believe what the best and most data tell us. If better data come along, we must be willing to change our views in accordance with the new evidence. Is science objective? Thomas Kuhn in 2012, a historian of science, argued that science as an activity conducted by humans is a social activity. As such, it is, according to Kuhn, subject to the same psychological influences of all human activities. Specifically, Kuhn suggested that there is no such thing as objective theory or data. All of science is informed by values. Scientists cannot help but let personal, cultural values, experiences, and opinions influence the types of questions they ask and how they make sense of what they find in their research. Kuhn's argument highlights a distinction between facts, information about the world, and values, beliefs about the way the world is or ought to be. This distinction is an important one, even if it is not always clear. To illustrate the relationship between facts and values, consider the problem of global warming. A vast accumulation of evidence, facts, substantiates the adverse impact that human activity has on the levels of greenhouse gases in Earth's atmosphere, leading to changing weather patterns. There is also a set of beliefs, values, shared by many people that influences their choices and behaviors in an attempt to address that impact. For example, purchasing electric vehicles, recycling, and bicycling. Our values, in this case that Earth as we know it is in danger and should be protected, influence how we engage with facts. People, including scientists who strongly endorse this value, for example, might be more attentive to research on renewable energy. The primary point of this illustration is that, contrary to the image of scientists as outside observers to the facts, gathering them neutrally and without bias from the natural world, all science, especially social sciences like psychology, involves values and interpretation. As a result, science functions best when people with diverse values and backgrounds work collectively to understand complex natural phenomena. Indeed, science can benefit from multiple perspectives. One approach to achieving this is through levels of analysis. Levels of analysis, the idea that a single phenomenon may be explained at different levels simultaneously. Remember the question concerning cramming for a test versus studying over time? It can be answered at a number of different levels of analysis. At a low level, we might use brain scanning technologies to investigate whether biochemical processes differ between two study strategies. At a higher level, the level of thinking, we might investigate processes of decision making, what to study, and ability to focus as they relate to cramming versus spaced practice. At even higher levels, we might be interested in real world behaviors, such as how long people study using each of the strategies. Similarly, we might be interested in how the presence of others influences learning across these two strategies. Levels of analysis suggest that one level is not more correct or truer than another. Their appropriateness depends on the specifics of the question asked. Ultimately, levels of analysis which suggest that we cannot understand the world around us, including human psychology, by reducing the phenomenon to only the biochemistry of genes and dynamics of neural networks. But neither can we understand humanity without considering the functions of the human nervous system. Science in context. There are many ways to interpret the world around us. People rely on common sense, personal experience, and faith in combination and to varying degrees. All of these offer legitimate benefits to navigating one's culture, and each offers a unique perspective with specific uses and limitations. Science provides another important way of understanding the world, and while it has many crucial advantages, as with all methods of interpretation, it also has limitations. Understanding the limits of science, including its subjectivity and uncertainty, does not render it useless. Because it is systematic, using testable, reliable data, it can allow us to determine causality and can help us generalize our conclusions. By understanding how scientific conclusions are reached, we are better equipped to use science as a tool of knowledge. Well, that was fascinating, don't you think? All that scientific thinking going on and thinking like a psychological scientist. It's important, like give yourself a little step back and look at the world a little differently. I find it quite fascinating. So if you like the show, share it with someone you know and hit that subscribe button. You don't want to miss the next chapter.